Chapter 8 marks a shift from discrete transistor amplifiers to integrated circuit, IC, amplifiers. While the fundamental principles remain the same, IC design imposes constraints and introduces opportunities that affect circuit implementation. Unlike discrete circuits, where resistors and capacitors can be easily added, IC design relies more on transistors and current sources to achieve biasing and signal amplification. A key advantage of IC amplifiers is that they can pack thousands or millions of transistors onto a single chip, making them more compact, efficient, and cost-effective than discrete circuits. This is the basis of nearly all modern electronics, from smartphones to medical devices. Some of the main topics covered in this chapter include IC biasing techniques using current sources and current mirrors instead of resistors. Basic gain cells in IC amplifiers including common source, CS, and common emitter, CE amplifiers with active loads. Current buffers and the role of common gate and common base amplifiers in signal processing. Cascoding, which improves amplifier gain and performance. Advanced current mirrors, which are used in designing high-performance analog circuits. 8.1 Integrated Circuit Design Philosophy. IC design has unique constraints and advantages that differ from discrete circuit design. Resistors are avoided. Large resistors take up too much chip space and are difficult to fabricate accurately. Instead of using resistors for biasing, IC amplifiers use transistors configured as current sources to establish stable operating points. Capacitors are limited. Large capacitors cannot be fabricated on chip, so IC amplifiers use direct coupling instead of capacitive coupling. Small capacitors, in the picofarad range, are used for frequency compensation and signal filtering. Low power supply voltages. To avoid damaging thin oxide layers in modern transistors, ICs operate at lower voltages, e.g., 1 volt to 3 volts instead of 12 volts or higher in discrete circuits. Low voltage design introduces challenges in biasing and gain performance. Transistor matching and scaling. Unlike discrete circuits, IC design allows for precise transistor matching, leading to stable operation. Bipolar and CMOS transistors can be combined by CMOS technology for better performance. These factors define how IC amplifiers are designed and optimized in modern electronic circuits. 8.2 IC biasing, current sources and current mirrors. In IC design, current sources are widely used instead of resistors for biasing amplifier stages. Basic MOSFET current source. A MOSFET current source generates a stable reference current for other transistors. The advantage is that bias currents remain stable despite changes in temperature or power supply variations. Current mirrors. A current mirror is a circuit that copies a reference current to multiple locations on a chip. How it works. A reference current is generated at one location and mirrored using transistors. Why it's useful. Ensures consistent biasing across multiple amplifier stages. Example applications: operational amplifiers, op-amps, sensor circuits, analog to digital converters, ADCs, BJT current mirrors. Work similarly to MOSFET current mirrors but use bipolar transistors. Provide higher gain and faster response compared to MOSFET versions. Advanced current mirrors. Wilson. Current mirror improves accuracy by compensating for transistor mismatches. Cascode current mirror increases output resistance, improving performance in high-gain amplifiers. 8.3. The basic gain cell, common source, CS, and common emitter, CE, amplifiers. At the heart of most IC amplifiers is the basic gain cell, which consists of a common source, CS amplifier for MOSFET circuits, a common emitter CE amplifier for BJT circuits, Why use current source loads?
In discrete circuits, resistors are used as loads.
In IC amplifiers, resistors are replaced with current sources, which offer higher gain and better performance. How gain is maximized. The intrinsic gain of a transistor is defined by its output resistance. Using current source loads increases gain, making the amplifier more effective. The early voltage plays a key role in defining the output resistance. Applications.
CS and CE amplifiers are found in almost all analog circuits, from audio amplifiers to microprocessors.
8.4 The common gate, CG, and common base, CB amplifiers. To improve amplifier performance, current buffers are sometimes needed. Common gate, CG, amplifier, MOSFETs, and common base, CB, amplifier, BJTs, act as current buffers. They increase gain and improve signal integrity by reducing unwanted feedback effects. Used in high-speed amplifiers and RF circuits. 8.5 Cascoding, a powerful technique for gain enhancement. A major limitation of basic amplifiers is their finite gain due to output resistance limitations. The cascode amplifier solves this by stacking two transistors, significantly increasing the output resistance and gain. The cascode current source follows the same principle, improving stability and performance in high-precision circuits. Real-world uses: high-frequency amplifiers in communication systems. Precision analog circuits where noise rejection is critical. 8.6 Advanced current mirrors. Beyond the basic current mirror, more sophisticated versions exist. Wilson current mirror provides better accuracy and higher output resistance, reduces dependence on transistor mismatches. Cascode current mirror combines the principles of cascoding and current mirroring, used in high-performance op-amps and analog circuits. 8.7 Pairing transistors for better performance. Differential amplifier stages are built by pairing transistors, ensuring better stability and matching. Improved performance in noise-sensitive circuits like biomedical instrumentation and sensor interfaces. Chapter 8 introduces the core building blocks of integrated circuit amplifiers. Instead of resistors and capacitors, IC amplifiers rely on current sources and transistors for biasing and gain. Current mirrors ensure consistent operation across amplifier stages. Common source and common emitter amplifiers form the basic gain cell in most IC designs. Cascoding improves gain and stability, making it a key technique in high-performance circuits. Advanced current mirrors and transistor pairing further optimize IC performance. This chapter lays the foundation for understanding op-amp design, signal processing circuits, and high-speed analog systems. Blast off! Thanks for watching this video. Be sure to subscribe, and I'll see you on the next one, Chapter 9, Differential and Multi-Stage Amplifiers.